We look at the night sky and see stars, planets, and galaxies, spread out in every direction like glowing jewels on black velvet. But beyond what we can see lies a deeper, more profound question. What is the shape of the universe itself? Is it curved like a sphere? Is it a saddle-shaped expanse? Or is it perfectly flat, stretching into infinity? The geometry of space may sound abstract, but it holds the key to understanding the origin, structure, and fate of everything. Let's explore the possible shapes of the cosmos and what each one means for our place in the grand design. What do we mean by shape? When we talk about the shape of the universe, we're referring to the geometry of space-time on the largest scales, billions of light-years across. Just like a sheet of paper can be flat, folded, or warped, space itself can bend and curve. The shape of the universe is determined by its density of matter and energy, especially dark energy and dark matter. There are three main possibilities, each with wildly different implications. 1. A flat universe. In a flat universe, parallel lines never meet. Geometry works exactly as we learned in school. The angles of a triangle add up to 180 degrees, and space extends forever. This doesn't mean the universe is two-dimensional or pancake-shaped. It means space is flat in 3 dimensions. According to the most recent data from the Planck satellite and WMAP, the universe appears to be flat to within 0.4% accuracy. This implies a perfect balance between the gravitational pull of matter and the outward push of expansion, a cosmic equilibrium. In a flat universe, the universe expands forever, but slows asymptotically. Light travels in straight lines. The cosmic microwave background, CMB, appears uniform and evenly spaced. But flat doesn't mean finite. A flat universe could still be infinite in extent. This is the current leading model in cosmology. 2. A closed universe, spherical. Imagine the surface of a sphere, but in 3 dimensions. In this model, the universe has positive curvature. Like the Earth, it's finite but unbounded. You could travel in one direction long enough and return to your starting point, assuming space didn't expand faster than you could travel. In a closed universe, parallel lines eventually meet. The angles of a triangle add up to more than 180 degrees. Light bends over long distances. The universe might one day stop expanding and begin to contract, ending in a big crunch. Some early observations hinted at this possibility, but more precise measurements have increasingly favored flatness. Still, small curvature can't yet be ruled out entirely. 3. An open universe, hyperbolic or saddle-shaped. Now imagine a Pringle chip or a horse's saddle. An open universe has negative curvature. It expands forever and accelerates faster over time. In this model, parallel lines diverge. Triangles add up to less than 180 degrees. The universe has no boundaries and is infinite in all directions. In a negatively curved universe, the cosmos would look increasingly distorted at extreme distances. This shape predicts a colder, more diffuse universe over time, ultimately leading to heat death and endless entropy. How do we measure the shape? To determine the shape of the universe, scientists use multiple tools. 1. The cosmic microwave background, CMB, as the CMB provides a snapshot of the universe just 380,000 years after the Big Bang. By measuring the angular size of temperature fluctuations, scientists can infer curvature. If the fluctuations appear larger than expected, space is curved positively. If smaller, it's negatively curved. If they match predictions, flat. Planck's data shows fluctuations exactly as expected in a flat universe. 2. Baryon acoustic oscillations, BAO. These are ripples in the distribution of galaxies caused by sound waves in the early universe. By measuring the distance between galaxies at different redshifts, scientists can detect curvature. So far, BAO data aligns with a flat model. 3. Type Ei supernovae. These standard candles allow astronomers to measure distances and expansion rates. By comparing observed brightness with predicted brightness, curvature effects can be detected. Again, flatness remains consistent with observations. Could the universe have a more complex shape? Yes, things get weirder. Even if the universe is flat locally, it could have a global topology that loops back on itself, like a 3D torus, donut shape. In such a universe, traveling far enough could return you to your starting point, but without any curvature. This is called a multiply-connected universe. Some researchers have searched for repeating patterns in the CMB that could suggest such a topology, like echoes of the same region viewed from different angles, but so far, nothing definitive. Still, the idea fascinates cosmologists. It would mean our infinite-looking universe could actually be finite and looped. Why the shape matters. Understanding the shape of the universe tells us how it began, how it evolves, how it might end. In a flat universe, expansion continues forever, eventually leading to heat death. In a closed universe, a big crunch or big bounce might follow. In an open universe, expansion accelerates endlessly, and galaxies become isolated islands in an ever-darkening sea. The shape also hints at what lies beyond the observable universe. Is space truly infinite? Or are we living in a cosmic hall of mirrors? And perhaps most profoundly, the shape tells us about the initial conditions of the universe and whether our reality was fine-tuned to exist at all. Final thought. We may never see the entire universe, but through careful observation, mathematics, and imagination, we can trace the curvature of reality itself, flat, curved, or twisted into something stranger. Space is not just where things happen. It is what happens. And here on Infinity Beyond, we'll keep following that curve to wherever it leads.